All right, let's dive into one of the most fundamental ideas in all of chemistry. Seriously, it's something that's happening inside your body and all around you right this second. This is the story of acids and bases.
So let me start with a question for you. What could vinegar, antacids, and your own blood possibly have in common? I mean, it sounds like the beginning of a weird joke, right? You've got stuff for cooking, something for heartburn, and the very liquid that keeps you alive. Where's the connection?
Well, you guessed it, the answer is acids and bases. From the lactic acid that gives milk its tang, to the bases in things like antacids and soap, these compounds are just everywhere. Even our blood absolutely depends on a super delicate acid-base balance to keep us going. So you see, to understand a huge chunk of our world, we've got to understand them first.
But, okay, what even is an acid or a base? You know, for centuries, scientists really struggled with this question. It wasn't some easy answer they just looked up in a book. Nope, it was a real quest, a scientific journey to find the perfect explanation.
And this journey gave us three big theories, each one building on the one that came before it. We're going to start with a guy named Arrhenius, who gave us a really solid foundation. Then we'll see how Bronsted and Lowry took a broader view, and finally, how Lewis came along with what's basically the master key to the whole thing.
So the first big breakthrough came from Svante Arrhenius, and his idea was beautiful because it was so simple. He basically said, look, when you dissolve something in water, an acid is anything that releases hydrogen ions, those little H+ particles. And a base, that's just anything that releases hydroxide ions, the OH- ones. A nice clean place to start.
It was a fantastic start, but you know how science works. It's all about pushing the boundaries and testing the limits. And pretty quickly, chemists found some weird situations where the Arrhenius theory it just didn't work. There were some major gaps in the story. His theory was perfect for classic stuff like hydrochloric acid. But then you get a chemical like ammonia. Now, ammonia clearly acts like a base, but if you look at its formula, NH3, there's no hydroxide group. There's no OH to release. The Arrhenius definition had totally hit a wall.
So, fast forward to 1923, two chemists, Bronsted and Lowry, came up with a brilliant new definition, totally independent of each other. They said, hey, let's forget about what gets released and focus on the hydrogen ion itself, which really is just a single proton. So in their view, an acid is simply a proton donor, and a base is a proton acceptor. Simple as that. And just like that, this new theory totally solved the ammonia puzzle. Look at this reaction. The water molecule actually gives away a proton to the ammonia. That makes water the acid in this case, and the ammonia, because it accepts the proton, is the base. Boom, problem solved.
But, believe it or not, the story wasn't quite over. In the very same year, Gilbert Lewis came along with the most universal definition of all. He zoomed out even further and focused on pairs of electrons. A Lewis acid is anything that accepts an electron pair, and a Lewis base is anything that donates one. This is a super powerful concept that covers everything the other theories do, plus tons of other reactions that don't even involve protons.
Okay, so now we have a pretty good idea of what acids and bases are. But that leads to a new question. Are they all the same? And the answer to that is a huge no. Some are incredibly powerful, and others are actually pretty gentle. Not all acids are created equal.
The big difference here really comes down to one word: dissociation. A strong acid, like the hydrochloric acid that's in your stomach, completely falls apart in water. It releases all of its protons, 100%. But a weak acid, like the acetic acid in the vinegar you have in your kitchen, is a lot more hesitant. Only a tiny fraction of its molecules actually break apart, and it creates this sort of balance, or what chemists call an equilibrium.
Naturally, scientists need a way to put a number on this strength. And that's where something called Ka comes in. It's the acid dissociation constant. And the logic is really easy. A bigger Ka value means more dissociation happens, which means you've got a stronger acid.
So for a really strong acid, you're looking at a Ka value that's bigger than 10. This is a substance that just can't wait to give away its protons. It dissociates completely, aggressively, no questions asked.
Now check out the contrast. For acetic acid, the K is tiny. I mean, look at that number, 0.000018. That tells you that it holds onto its protons really, really tightly. Only a teeny tiny amount of it actually breaks apart in water. The difference in scale here is just massive.
And this leads to a really cool, kind of counterintuitive idea called Ostwald's dilution law. Get this. For a weak acid, the more you dilute it with water, the greater the percentage of its molecules that will actually break apart. Isn't that wild? Making the solution weaker actually encourages more of it to ionize.
All this talk about constants and dissociation is, well, it's pretty theoretical. How do we actually use this in the real world? We needed a simpler tool, kind of like a ruler for measuring acidity. And that is exactly what the pH scale is.
The term pH literally stands for power of hydrogen. What it does is take these tiny, awkward numbers for concentration and turns them into a nice, simple scale, usually from 0 to 14. But the key is that it's a logarithmic scale. That means every single whole number jump is actually a massive 10-fold change in acidity.
So a low pH, like 1 for battery acid, is crazy acidic. A high pH, like 13 for drain cleaner, is extremely basic or alkaline. And right there in the middle, at a perfect pH of 7, is neutral. Think pure water. And remember, the difference between vinegar at pH 3 and pure water at pH 7 isn't just 4 times, it's 10,000 times more acidic.
You know, this is a really powerful way to think about it. Just like a thermometer gives us a simple number for something we can feel, heat, the pH scale gives us a simple number for the invisible power of acidity. It makes a really complex chemical property super easy to understand at a glance.
So we've been on quite a journey, right? From old school definitions to modern measurements. But let's circle all the way back to our first question. Why is this so important? Why does any of this stuff really matter?
It matters because these substances are quite literally the workhorses of our world. In our bodies, our blood's pH has to stay in an incredibly narrow range just to keep us alive. In industry, huge amounts of acids are used to make everything from fertilizer to plastics. And, right at home, it's basic compounds that make our soaps and cleaners work.
And that brings us to one final, really critical thought. Your body is in a constant, invisible fight to keep your blood pH right around 7.4. All that complex chemistry we talked about, proton donors, electron acceptors, it's all happening every single second inside of you just to keep that number stable. Which leaves us with a pretty important question. What happens when that delicate chemical balance fails? That's when chemistry stops being theoretical and becomes a matter of life and death.